inclined plane of science. We can use it to see how objects travel on a slanted surface, as well as the different forces that they interact with on their way down.
So let's get to work. So let's experiment with a couple objects for 1 and 2 different configurations to see how they roll down this slanted slope. In this configuration, the ring is going to slide. But in this configuration, it rolls. So what makes the difference? Well, for an object to rotate, it needs torque. Torque is a force that acts on an object at a distance from its center, while gravity is a force that acts at a mass at its center. So, what can be a force that acts at the point the ring meets the plank? Yeah.
I got it. Friction. Yep. Friction provides a torque that causes an angular acceleration, along with the linear acceleration caused by gravity. When an object rolls without slipping, we need to take both forms of energy into account. Not only the rotational kinetic energy here, but the translational kinetic energy from our gravitational motion.
For rotational motion, we need to account for more than just mass. Rotational motion is affected most by the distribution of the mass within an object, the moment of inertia, or rotational inertia. This is why a disk, ring, and sphere with the same mass and radius can roll at different speeds down a ramp. They have different moments of inertia because of their different shapes. Here are some of the formulas. Note that they're affected by mass and radius. In translational motion, kinetic energy is represented by this formula. But to get to the formulas for rotational motion, we substitute mass and velocity for the rotational components, moment of inertia, and the angular velocity. So now we have our basic concepts, and we can put them together.
Alright, so let's put everything together. Here we have our little basic setup, our hypothetical rolling motion problem. So we have, let's call it a disk, and it's on an incline, it's about to start rolling down this incline. And so we can use the law of conservation of energy to pull everything together. So, as we remember, the law of conservation of energy is that your total beginning kinetic and potential energy, add those up, so initial kinetic energy plus initial potential energy equals final kinetic energy plus final potential energy. But now we have to factor in the fact that not only do we have rotational kinetic energy, but we have translational kinetic energy, right? Because you have your frictional torque and you have your gravitational pull as normal. So, if we're assuming that we're starting from here, then we know that our initial kinetic energy is 0. And our if we're going all the way down to the end of the hill or incline or whatever, then our final potential energy should also be 0. So, if we're going from here, we're going to call this our height. So, initial potential energy is going to be mgh. And then we have two types of kinetic energy. We have our translational, 1/2 mv squared, and our rotational, 1/2 I omega squared. So we're going to put all of this together. So we have mgh, our initial potential energy, equals 1/2 mv squared plus 1/2 I omega squared. And so using your laws of angular kinematics that you should already know, you can sub in maybe, what is it? You can sub in the required variables and convert this omega into a linear form, or you can convert this velocity into an angular form, whatever you need to do to solve your equation. But this is your basic framework, and with that, you can figure out whatever you need to figure out.